Hello, my name is David Block, and what I'd like to speak with you about today is accelerating fermentation to use resources more efficiently during harvest. And when I'm talking about resources, I'm mainly talking about resources like fermenter space. In order to talk about that, I'd like to break my talk into 4 parts. First of all, I'd like to start with the idea of process intensification and define that so that we can understand why it might be an important thing to do in a winery setting. Next, I'd like to kind of back up a little bit and talk a little bit about how nitrogen is being used by yeast during fermentation. It's kind of a review of work that we did years ago, but it sets the stage for talking about intensifying the white wine fermentation process, being able to finish that process in significantly less time than using a normal process, and look at what impact that has on the final wines. And finally, I'd like to talk about intensifying the red wine processing process and talk about whether that can be sped up as well, especially in phenolic extraction. So that's the game plan for the rest of the talk. So let's start with a definition of process intensification. And the definition that I'm giving here, and this is a well-known term in the chemical engineering world, is process intensification is accomplishing a process like winemaking in a lot less time or with a lot less equipment without impacting the outcome of the process in any kind of negative way, thereby reducing either the capital costs, the amount of equipment you need, or the operating costs, how much it costs you to do the processing, substantially, or maybe even both, the capital costs and the operating costs. So the idea is, how do you actually make your process more efficient so you can do it in less time or with less resources? So that's what we're going to focus on today, and I'll talk to you about various ways that we're working on to intensify the winemaking process. So this is just a picture of an atypical winery, granted, but you can see all the equipment here. And let's say in this winery, they wanted to expand even further. One way would be to build out even more equipment. But if you can actually accomplish the processing in, let's say, half the time, do the fermentation in half the time, you may actually be able to use the tanks more times than in a typical season. And this would give you more capacity with the same amount of equipment. That's the idea of process intensification. All right, so let's back up a little bit before we talk about how we might intensify, let's say, a white wine process, or at least the fermentation kinetics of a process, whether it's red or white. And I want to back up and talk a little bit about the role of nitrogen in wine fermentations. How is the nitrogen used by yeast, and how does varying the nitrogen level affect yeast fermentation kinetics? Well, years ago, more than 20 years ago now, we developed a mathematical model for wine fermentations. It kind of describes how yeast use nitrogen. So in this model, there are 4 equations, one for yeast, one for nitrogen, one for sugar, and one for ethanol. And the details of this are not important, other than to say that the growth of the yeast is dependent on the specific growth rate, which is defined in terms of the nitrogen concentration. And so, therefore, when the cells run out of nitrogen, this end term will go to 0 and they'll stop growing. So in other words, the wine fermentation is nitrogen limited. If you add more nitrogen, you get more cells and the fermentation will go more quickly. It's more likely to finish before getting sluggish or stuck because the cells will spend less time in the alcohol, the ethanol, being inactivated. Okay, so the idea is, again, that the more nitrogen you have, the more cells you're going to get. And if you put that model, integrate that model, this is what it predicts. The nitrogen curve here is a little hard to see, but here's the nitrogen utilization curve. And you can see as the nitrogen is utilized, the cells grow essentially exponentially, which is what you'd expect for yeast. And then when the nitrogen runs out here at about 30 hours, the growth stops. Okay, so it's nitrogen limited fermentation. You can see most of the sugar utilization doesn't start until almost all the growth is done and the nitrogen is utilized, and then the sugar gets utilized, and proportionally you get production of ethanol. When the sugar is gone, your ethanol stops going up in concentration. The cells, after they reach this point of maximum cell growth, start to become inactivated by their presence in ethanol. So if we look at what that does to nitrogen, and this is some experimental data with a model overlaid, there's a lot of scatter in these dark circles, closed circles. What we can see is, and these are Brix curves, is this is a very low nitrogen level, about 30 or so milligrams per liter of nitrogen. And you can see essentially there's almost no growth, no utilization of sugar, because so few cells are formed in this process. As you increase the nitrogen level, you get progressively faster fermentations because you have more cells. At some point, you can add more nitrogen and you don't get a faster fermentation, and probably because something else becomes limiting in the grape juice. All right, so this just again illustrates that nitrogen is limiting. So if nitrogen is limiting and you're going to have a fermentation that's, let's say, destined to stick, and this is the sugar curve, this is the model predictions, it's destined to stick. The question is, well, what happens if you add nitrogen in the middle of the fermentation, which many of you probably do as a standard practice, to add nitrogen sometime in the first day or so of the fermentation. And what you can see is, here is the normal cell growth. And as soon as you add nitrogen, you will get a burst of cell growth. That's the prediction. And the fermentation will all of a sudden speed up. And that's because, again, immediately when you add the nitrogen, it's used. So here's the nitrogen. You can see it's used. It goes up quickly, gets used quickly, and at the same time, you get this burst of cell growth. And so what these curves are is if the prediction of if you added nitrogen, say in the form of DAP, diammonium phosphate, at different times during the fermentation, you can see that the prediction is that you would actually save that fermentation. So we did that experimentally, and when I say we, this is Julie Schreiber's master's thesis from a little over 20 years ago. And you can kind of see the same thing that's predicted here. And if we look a little more closely, because it's a lot of data, you can see that when the nitrogen is added, and each of these represent nitrogen addition at a different time, you can see, so here in this case with the squares, the nitrogen is added right here, and you can see an increase in the cell concentration. There's a slight increase in the rate of sugar utilization. But interestingly, if you look at the nitrogen utilization in these cases, you get what's predicted by the model up until about 200 hours, until the addition here at 120 hours. Very fast use of nitrogen, increase in cell concentration, increase in sugar utilization rate. But out here past 300 hours, at 360 hours, when we add nitrogen, nothing actually happens. And the reason that nothing actually happens is none of that nitrogen is taken up by the cells, probably because the cell membrane of the yeast has changed and isn't allowing transport of nitrogen anymore into that cell. So there are some limitations on whether nitrogen additions can help you with your fermentation, help it to finish faster. Of course, that experimental data was with addition of diammonium phosphate, but if you add different kinds of nitrogen, you'll see slightly different data. In this case, we added superfood, which is a combination of diammonium phosphate and organic nitrogen. And what you can see is if we zero in on the cell concentration, you see almost exactly what the model predicts. As soon as you add that extra nitrogen, you get a burst in the cell concentration, get a speeding up of the nitrogen, of the sugar utilization curve, the Brix curve. And if you look at, even at the latest time, additions at 360 hours here, you still see this increase in cell concentration. And if we look at the nitrogen, because we added organic nitrogen in this case, some of that is actually still taken up by the cells for whatever reason. And so when we're adding more complex nitrogen source, we actually see, even late in the fermentation, we see an increase in cell concentration and a speeding up of the Brix curve. I will also note, and this is work done by Russ Fish and Matt Coleman in my lab, that having nitrogen there in the media, enough nitrogen in the media, actually gives you more flexibility on temperature as well. And so if you wanted to run at low temperatures, and you want to avoid a really sluggish or stuck fermentation, then actually having more nitrogen will help that be a possibility. And that's what these data show as well. Whether it's very high temperature, very low temperature, having more nitrogen gives you a more successful fermentation across a much broader range of temperatures. All right, so with all that in mind, I want to talk a little bit about, is it possible to get, let's say, a white wine fermentation, a Chardonnay fermentation, to actually finish much faster than it normally would at whatever temperature, 15 degrees Celsius, 60 degrees Fahrenheit, something like that, or whatever the winemaker is looking for. And so again, this is the idea of process intensification. All right, so let's take a look at whether we can intensify the fermentation kinetics. In other words, have the sugar be used faster, significantly faster in fermentations, without changing the temperature. Of course, we could speed things up probably by increasing temperature, but that can lead to problems in the kinetics further on, like a stuck fermentation, and can change the sensory attributes of the wine. So let's see if we can actually intensify the fermentation process, keeping a low temperature, but just by adding nitrogen in a systematic way. So this is work by Conrad Miller in my lab a couple of years ago. And what he did first was he ran 4 sets of flasks, Erlenmeyer flasks. So these are 400 milliliters of Chardonnay juice with EC118 yeast in a 500 milliliter flask with an airlock. And he had 4 different combinations of inoculum size and initial nitrogen. So the control was the standard nitrogen that was in that Chardonnay juice of 310 milligrams of nitrogen per liter, which should be fine for finishing fermentation, and a standard inoculum of 0.25 grams of yeast per liter. Then he used the same inoculum, but with 1,100 milligrams of nitrogen per liter, using Fermade as a nitrogen addition. And then he also tried adding a much higher inoculum of 10 grams per liter with the standard nitrogen level, or both, adding a lot of cells and a lot of nitrogen to see what happens. And these are the data in this table above. What you can see is when he started with high biomass, 10 grams per liter, the fermentation finished significantly more rapidly than starting with the standard label amount of yeast. You can see when he added high nitrogen, even with the low biomass, he still had a faster fermentation, not nearly significantly faster, but faster than the control. So adding more nitrogen or more cells and nitrogen, all of those things finished faster than the control. Maybe more importantly for this work, what Conrad then did was he took the data from all those fermentations, and he had measured the optical density, the cell concentration. He had measured the sugar concentration at any given point and the nitrogen concentration, and he made this curve. And what this curve is, you can see on the x-axis is Brix. So this is where in the fermentation you are, how far along in the fermentation. And the y-axis here, and you can see this on a logarithmic scale, is actually the nitrogen utilization rate at normalized to the cell concentration and the nitrogen level at the time at any given point in the fermentation. And what you can see is as you get further and further along in the fermentation to lower and lower Brix, in any of these fermentations, the nitrogen utilization rate slows down dramatically, partly maybe because you don't have as much there, but also, as I showed in the data previously, probably because the cells start becoming inactivated and they just can't take in the nitrogen at all. So what Conrad did is he drew a straight line through this, a regression line, and he found this equation here, which is an exponential function. And he integrated that over the course of the fermentation. Instead of using time, he used Brix, and he got this equation here. And what this equation is N now is the amount of nitrogen that's predicted to be able to be used from that point of the fermentation to the end of the fermentation. So it's going to be higher at the beginning of the fermentation than at the end, and it's going to change over time. And so what you can do with this equation is at any given point in the fermentation, you should be able to calculate N now based on the Brix level and the OD. And after you've calculated that, you should be able to measure how much nitrogen is in the fermentation. And assuming the N now is greater than what you have, you could add that differential, adding that more nitrogen, and get more cells to grow in a faster fermentation. And if you do that constantly, you're continuously adding nitrogen to get the most cells in the fastest fermentation, but doing it in a way that you're not going to end up with a lot of extra nitrogen at the end, which can be problematic from a stability point of view. All right, so that's the idea. Let's see whether it works or not. In order to see whether it works, Conrad did fermentations in our TJ fermenters, about 120 liter working volume with Chardonnay juice. And he had 3 treatments that he tried out. The first is control. He added the normal amount of yeast and didn't adjust the nitrogen after the beginning of the fermentation and just let it go. All right. And that's this blue line right here. That's the Brix curve. And you can see it took about 10 or 15 days to finish at a cold temperature. And these were done at about 60 degrees Fahrenheit, 15 degrees Celsius. The next thing that he did was he used that equation I just showed you on the last slide. He started with a normal amount of cells, like the 0.25 grams per liter of cells. But at every 12 hours, he calculated that N now, and he made an addition based on whatever nitrogen was in there to get back up to the N now level, again, every 12 hours throughout the fermentation. That's what he called semi-batch. And that's the orange curve here, and we'll come back to that in a second. And then the last thing he did was he took an idea. He had spent some time in the brewing industry where they tend to repitch yeast, reuse yeast. And he actually grew up some yeast on grape juice, harvested that yeast, and added that. So he had much higher inoculum and did the 12-hour measurements and nitrogen additions, both to see if he could speed up by having that much higher inoculum, to see if he could speed up the fermentation even more. And so if you look at what the results are, they're actually pretty dramatic. The blue curve is the control, and you can see it reaches 0 Brix around 250 hours and reaches dryness about 300 hours or so. If we look at where we just added nitrogen every 12 hours, using that equation in the previous slide, you can see that we've actually cut the fermentation time almost in half. So we get down to dryness at about 150 hours compared to 300 hours, where to 0 in about 0 Brix in approximately 40% reduction in time. Very significant reduction in time without changing the temperature. If you look at the third treatment where he did that nitrogen, 12-hour nitrogen additions, using the equation on the previous slide, but also started with a much higher inoculum. Here you see the optical density of this treatment compared to the others. You get an even faster fermentation. And here you get to dryness at about 100 hours, 1/3 of the time it took to get to dryness in the control. So you can see how this approach really, truly intensified the process. And what that would allow us to do is turn around these tanks in half the time or even 1/3 of the time of the control. So significant ability to take, let's say, take that juice out at dryness, put it in a storage vessel or barrel or whatever, and reuse that tank much, much sooner than if you allowed it to go in the normal control process. So this is the idea. Now, I think one of the things that you really have to think about, because this is wine, is how does that affect the fermentation and the chemical and sensory characteristics of the wine. So first thing this shows some of the data on the different fermentations, and interestingly, actually reached a lower sugar level at the end with the two experimental treatments versus the control, but all of those would be dry anyway. We were shooting, that equation shoots for getting the nitrogen at 30 milligrams per liter or less at the end. And you can see that that's true of all three of those, though the residual nitrogen in the control is a little bit lower than the other two, but they're all below 30 milligrams of nitrogen per liter. You can see the cell concentrations at the end are much higher in the experimental treatments versus the control. And as you would expect, the sugar utilization rates are significantly higher in the experimental treatments versus the control. That's what I showed you on the previous slide. One of the things that we worried about when you add a lot of nitrogen is the appearance of ethyl carbamate, which is something you don't want in your wine, which has health impacts. So we actually sent all of these fermentations, samples from all these fermentations out to for analysis for ethyl carbamate, and all of them came back with none detectable. So that's really good news that we can do these treatments and not have to worry about the safety of that wine afterwards. So the next thing we did was collaborate with Anita Oberholster's lab and Raul Girardello in her lab, and he did GC mass spec with Conrad to look at volatiles and to see whether the volatiles that we could measure were impacted. So this is the idea of, these are things that would probably impact at a high enough concentration, impact the aroma of the wine. And of all the things that we measured, the ones that were significantly different between the treatments, and here's the control, the semi-batch, and the recycle semi-batch, are the ones in bold. So 1, 2, 3, 4, 5, 6, 7 were somewhat different. And interestingly, the isobutanol was a little bit higher in one of the treatments, experimental treatments versus the control. For the most part, anything else that was significantly different was actually lower in the experimental treatments versus the control, nitrogen feed versus the control. Although I'm not sure whether these, one of the things you have to ask yourself is, did these treatments, even though they're different chemically, are they different from an actual sensory point of view? Can humans sense the impact of these chemical differences? So with Hildegard Heymann's lab and Annegret Cantu, we were able to do a detailed descriptive analysis of all of these wines. And the panel picked out 19 sensory attributes, both aroma and in the mouth. And interestingly, of all 19 of those attributes, only 2 of them were significantly different, statistically significantly different in the experimental treatments versus the controls. So for the most part, the aromas in all these wines were identical. Now, the 2 sensory attributes that were different were ones that are related to sulfur, descriptor of sauerkraut, and another descriptive of sulfur or egg, again related to sulfur compounds. And if you look at these in the descriptive analysis, actually there's some overlap between the control and the semi-batch, but there is some significance to those differences. There's more of a difference with the recycle semi-batch. And if we look at a PCA of the significantly different chemical terms and sensory terms, what you can see is the recycle semi-batch, so the one where we repitched yeast and did a nitrogen feed, are the ones that are most associated with that sulfur and sauerkraut, less so with semi-batch, and the control had less of those things. some degree. Again, there's some overlap. These differences are not huge, but they are statistically significant. So there's a little bit of difference in those two terms and no difference in 17 of the 19 sensory terms that we picked out, that the panel picked out and rated the wines on. Okay, so what that says is, just kind of summarize that part, is that for the most part, we can accelerate the process quite a bit without impacting the sensory characteristics of the wine really significantly. And I think that's really important because it means that maybe we can intensify a wine process just by the way we feed nitrogen almost continuously during the fermentation, at least every 12 hours or so. So I think a big opportunity there to use your equipment more efficiently and even increase capacity without increasing the number of fermenters, and still have a really great product come out. Okay, so again, more work could be done there, but it gives an idea of what can be done. One of the things that we thought about is, well, could you do this for red fermentation? And I think the answer is probably yes, although we didn't try it with the nitrogen additions. But it does beg the question of, if you can finish the fermentation quickly, but you still need the skins in contact with the liquid, does it really save you anything? So I did have a student, Anna Yao, who worked with me and with Conrad Miller on investigating whether we could intensify the phenolic extraction component of the wine, of a red wine. And this is work with Anita Oberholster as well. And the idea, and I'm not going to spend a lot of time talking about this because we haven't done as much work in this area, but the idea is, what if when the grapes came in, you crushed them, you separated the juice and the skins, you fermented the juice quickly, like I showed you with the intensified process, you put the skins, let's say, in a column, and then you flow either juice or wine through that column continuously, and once through, and that's your extraction. So you can see, actually, here's the experimental setup that Anna used. Here's the pump. Here's the column with the skins in it. This is a pretty small scale. And the colored juice coming out. We did a lot of work with this, and some of it was promising, some of it was less so. But I'll just show you one of the promising sets of data that Anna collected. And this, she took grapes that came in that had been frozen for a while. She did a fermentation in a bucket, so not a very controlled fermentation. And she looked at extraction of anthocyanins and tannins over time. So here's the anthocyanins, here's the tannins. And then she also continuously pumped juice from the same set of grapes over skins in a column, basically in a circle, so in a closed loop, and checked over time the extraction. And what she found was that the anthocyanins actually reached the same level as in the bucket in about a third of the time, and the same thing with the tannins. And so what we saw here, again, a lot more work needs to be done on this, is that it might be possible to accelerate phenolic extraction as well. And then you could imagine this idea of really speeding up the yeast fermentation part, the alcohol production part, by nitrogen addition, and speeding up the extraction part by extracting in a novel way, like flowing the juice or maybe even the finished wine through the skins either once or maybe several times in order to get the extraction that you desire. So, in thinking about this, it also kind of points to some other ideas that are either we're thinking about or other people in the department are working on. And this idea of, could you actually speed up everything post-fermentation, whether it's extraction or anything else, and using something that's more akin to continuous processing? So just as a conceptual idea, what if you finished your fermentation really quickly using nitrogen feeding, and then you fed that through a column packed with the skins to get a phenolic extraction. And then maybe you took that and you had it flow through a column with oak chips to get your oak impact in a short period of time. And then maybe you flow through an ion exchange column to do any protein finding. This is an idea that Ron Runenbaum is working on. And then maybe at the end you flow it through a tartrate bed to do cold stabilization, another idea that Ron is working on, and end up with a finished wine. And this is kind of a one shot where you send it through each of these columns in series and go from a very unfinished wine to a finished wine in a short period of time. So this is just an idea. It's a direction. We're working on some of these things, not working on others, but it's just a concept of how could you intensify the process, the whole process, and not just the fermentation that I spent most time talking about. How likely is this? Well, in other allied industries, they're already doing this. If you've ever had the opportunity to enjoy Torpedo, the extra IPA from Sierra Nevada, this is exactly what they do. And if you go online, you can see them. They have pictures of this. They basically take this metal column, they fill it up with hops, and to get a lot of hops of extraction, they basically pump the beer through that hops column to get even more hops extraction. Okay, so it's a very similar kind of industry and a very similar kind of idea to what I just discussed. So it certainly is a possibility. All right, to summarize, yeast fermentation can be sped up dramatically through smart nitrogen feeding. The idea that Conrad used, measuring nitrogen every 12 hours and adding enough using that equation that I gave so that you'll speed up fermentation but won't have residual nitrogen at the end. And we saw that we could speed up the fermentation by anywhere between half and 2/3 without that much impact on the sensory characteristics. 17 of the 19 characteristics judged by the panel didn't change at all. And then you had 2 where you did see minor changes, and you have to decide whether that would be significant for your wine or not. Doing this kind of intensification could really help you with your winery capacity, because if you can get wine out of fermenters faster, you can turn them around more times and increase your production without increasing the number of fermenters you have, which are going to be, expensive capital. And at the end, I mentioned that it's also possible that other winemaking processes, whether phenolic extraction or any post-fermentation process, might be able to be intensified as well. Again, with the idea that you can create the same amount of wine with the same or better characteristics using fewer resources or in less time. That's the whole idea of process intensification. So with that, I'd like to fund the sources of funding for this work. American Vineyard Foundation, Ian J. Gallo, and the Ernest Gallo Endowed Chair. And the people who actually did the work, especially Conrad, Miller, Raul, Annegret Cantu on the sensory part, and Anna Yao on the phenolic part. And my collaborators and people who worked on some of the data that I showed you from a while back. Actually, I realized Julie Schreiber's name isn't on here, but she should be on there as well for some of the early work on nitrogen additions. So with that, if you have questions, I'm always happy to take questions. This is my email here. You can email me any questions you might have, or if you'd like to discuss this further. Thank you.